Alright, let's summarize for PCA. PCA. Basically, we started with this situation and then we created another coordinate system which we called A1, A2. And we did a PCA transformation. What PCA actually does is first mean normalization. So it will bring the data. This is again x1, sorry. It will bring the data centered around a mean of 0. And the axes now become z1 and z2. A are the unit vectors of these z vectors. So what does PCA do is a mean normalization. So it centers the data around 0 and then it projects data onto axes with maximum variance. Okay, so in this case is the z1 axis. You could basically say that maybe z2 is not important enough. Imagine you have a situation like this one, where it's something like this. In this case, you could say that the variance in the z2 direction is not so important, and you can drop that dimension. This is the idea of PCA. Now, how much variance do we retain? Remember that I said, and this is not a normal distribution, I'm just showing you a normal distribution because it's easy to explain. Remember we had the data, something like this. We had a mu mean and we had a standard deviation sigma. Mu and sigma totally define this data distribution. Totally. So what PCA does, first it brings the mu to 0. It does mean normalization. So we have here. So the mean is 0 and the sigma, we try to keep it as high as the initial sigma. Initial meaning before PCA. If we're able to do that, we represent the data correctly in less dimensions. Okay, now we have seen that our first eigenvalue was lambda, the second one was alpha. So basically, let's call them all lambda, and you have lambda 1, lambda 2, all the way to lambda d. You have d, and these dimensions, d eigenvalues. So what we try to do is, we try to reduce the number of dimensions, for example, here, up to lambda k. So that we want to retain the maximum dimension. So in the denominator you have lambda 2 plus all the way to lambda d, and in the numerator you have lambda 1 plus lambda 2 plus lambda k. And you only retain k principal components out of the d dimensions. And what we look for is that so this is smaller than 1. And what we look, so k principal components, right? K principal components. We try to retain ideally 99% of the variance. If we retain 99% of the variance, we're very solid. Eventually you could go down to 85% if you wanted to, yeah? But we should aim for 95-99% of the variance retake. Okay, that was PCA.